So we have two types of operations. The first type is you forget that this is a quantum state, and you just apply a classical operation to that. So we have classical reversible operations, which are going to apply independently on all the basis states here. So you transform X into whatever, and you apply this in superposition to all the elements of this state. And the second type of operation we use, and basically we've done everything with that, is Fourier transforms over the amplitudes of the quantum state. Now, this is where we can gain some power from quantum computing. So imagine that the amplitudes of your state would be the values of the outputs of some function. You can take almost for free the Fourier transform of these outputs. So we obtain a state in which the amplitudes are now the Fourier coefficients of the function. And in our case, because it's super simple, we can have the Fourier transform over F2, which is called the Hadamard transform. Also, to make it even more simple, we're going to avoid writing the normalization of these amplitudes, because they have to be normalized since there are probabilities. But we're going to simplify that a bit. Okay, so these are two operations we use, either transforming the basis states or transforming everything by taking Fourier transform. Now, we've known for quite a while that when we go into quantum attacks on symmetric crypto systems, we need to distinguish between two adversaries. The first one would be the most standard one, so to say, which is the so-called Q1 model, in which indeed the adversary has a quantum computer, but the access to data, the access to the key, the secret key oracle, is classical. That means the access to the data hasn't changed, as before, but we just have more computing power. And the second one is strictly more powerful, and that's the superposition setting, so-called Q2, in which the adversary is quantum, but now you take the black box, the secret key black box, and you put it some kind of inside the quantum adversary, like inside the quantum computer, and you can access it as a quantum oracle. So instead of simply encrypting a classical plaintext, you encrypt a quantum state. And in our case, this is how we write that. It happens that this model is capable of breaking many constructions that are secure in the Q1 model and in the classical setting, of course. And that's what makes it interesting. Of course, it doesn't have really applications in practice, but it's interesting to see how much we can go into breaking things if we allow superposition attacks. And this is the topic of this paper. So the typical way we use these superposition attacks to break things is by using Simon's algorithm. So I will just do a brief recap of what Simon's algorithm can allow you to do, but I won't detail this algorithm because we want to use it in the end. So consider the following very, very simplified case where you have some kind of, some kind of cipher which absorbs a key first into the internal state, and then absorbs some plaintext X using an XOR, and then you post-process this with a function that is not invertible. So you obtain some J of X plus something depending on the K. Okay, if you have access to that, you will have access to a shifted version, so to speak, of the function J. So shifted by some hidden shift S, which depends on the key and that you don't know. So recovering the hidden shift will be supposedly a difficult problem, but with Simon's algorithm, you can do this pretty efficiently. So the boilerplate is that with one quantum query to G and one quantum query to J of X plus S, so the shifted version, you can recover 1 bit of the secret. So if you do that n times, you basically recover the whole secret. And this makes the algorithm very efficient. And this is I would say this is the main idea behind most of the Q2 attacks on symmetric constructions, where you can embed some kind of hidden shift or hidden period that you can recover immediately by launching Simon's algorithm on this. Okay. But we're in a setting where, as I said, we are targeting AE schemes and they are nonce-based. So we should first make sense of a Q2 model in that. Because if the scheme is nonce-based, then you can't repeat nonces. Whether you have classical or quantum queries doesn't matter. If you repeat nonces, it's already broken. So not interesting from a quantum attacker point of view. So the model we use, which is actually pretty standard, is that the nonce is indeed a classical value, and indeed it's not repeated. Meaning that each time we make a quantum query, we just have to take a new nonce. You can imagine that the nonce is still adversary controlled, but we just have one quantum query that is allowed, and then that's it. Change the nonce. So this is the model we are considering. And now I can properly introduce the problem we're going to have. The problem is that the nonce changes, so the period is going to change. The hidden shift is going to change. So imagine now that I've modified my previous simplified case, and now you have an internal state which absorbs the nonce and the key. And you still have this plain text, the plain text we control that is exort to that. And then we have the post-processing that is not invertible, so we just observe some shifted variants of the function g. And now we have a shift that depends on the nonce. But I said before, if you use Simon's algorithm, you get only 1 bit per quantum query. And now we have only 1 quantum query, which means we get 1 bit of the shift, and that's it. Allow us to recover this entire hidden shift with only a single quantum query, which is what we do in this paper. So now I will try to present the idea of this different quantum algorithm in a very high-level way. And yeah, let's start. So first of all, the exact setting is that you will have a function, which is a Boolean function, but remapped on -1, 1, because we like to work with complex numbers. And then we are allowed a single query that puts the value of this function into the place of the state. So basically, we just put a -1 or a 1 in front of the basis state x. And the question is, can we recover S? The answer, of course, is yes. As usual, this is a quantum algorithm that has been known since like 10 years, and we've waited a long time to use it actually in cryptanalysis. So that's an algorithm based on what it's called quantum rejection sampling. Okay. I will just give you the algorithm and explain it a bit. So we start from a uniform superposition of everything. So we take all the possible input x and we put this into a quantum state. That's, of course, where we have some quantum advantage because we can query now the shifted function on all possibilities in superposition. So we call our oracle and we obtain this quantum state with the shifted function. And once we do that, the standard thing in quantum algorithms is just to put Hadamard transforms, like Fourier transforms of the amplitudes, and try to see what happens. So we do Hadamard transform, and we can start to notice that if you do the Hadamard transform of the shifted function, you obtain almost the Fourier coefficient of the function, but then you have this -1 y dot s term that appears. And now the idea would be to remove the Fourier coefficient of the function by some kind of, multiplying by this inverse of it. And the state that you get is exactly the Hadamard transform of the secret S. That's super nice, because now you just measure that and you're done. That's it. That's the algorithm. It was actually quite simple. And indeed, the S algorithm contains only one call to the oracle. So we're done. So of course, if you're not very used to quantum computing, all of this might seem a bit strange. But if you're used to quantum computing, it will be even weirder, because this operation here is not legal. You can't just multiply the amplitudes like that. First of all, because it's not unitary, so it's simply not allowed. The trick is that this is not allowed, but applying a non-unitary operation simply means that it will succeed only with some probability. And it is actually possible to compute this, even though I won't do the details here. The only thing you have to do is to be able to compute this Fourier coefficient j hat of y, sorry, that you are trying to remove here. And also you need, I mean, you will have some trouble if the Fourier coefficient is 0. I won't even talk about that. But to make it the most efficient possible, we need to have some kind of approximate version of this operation. And we're still going to be able to obtain approximately the state we're looking for at the end. So yes, this is the algorithm we use. It has a single Pareto shifted version. That's nice. It needs to compute a Fourier coefficient. That's not nice, because it means if we have a very complex function, it is going to be quite difficult. And this is why, in some cases, it's much better to use Simon's algorithm. So in our case, we need G to be quite a simple function. And of course, we also have some probability of success that we need to compute, and everything will depend on the function G in the end and its Fourier transform. Now I will show you an application of this, the simplest one we had in the paper. So try to connect the algorithm that I just presented with, actual cryptanalysis. So let's look at Tioxin 346, which was a candidate on the CESAR competition for AE schemes. And it's based on the AES. So since this is the last session, maybe I could skip the presentation of the AES, where every state is a 4x4 matrix of bytes, and then you have an AES round composed of a sub-bytes operation applying to S boxes, and then a linear operation. The internal state in Tioxin is quite large because it's 13 times an AES state. The round function is applying some AES rounds on this internal state and absorbing some message blocks that you input. And let's focus on the initialization and encryption part. So when you initialize, you just load the key and the nonce in the internal state. When you encrypt, you absorb the blocks, and then you output ciphertext blocks. And then there is a finalization because you need to output a tag, but we just focus on the encryption. The ciphertext blocks have some expressions that depend on the current values of the internal states. We need to find some hidden shift in that, which will depend on the key and the nonce. So we do that. We just look at the expressions of some ciphertext blocks. The initialization rounds, and we can go back to the key. So if we're able to recover T3 at any point of the algorithm, we finished. We can recover the key and we're done. So that's the goal. Okay, let's find some hidden shifts. Of course, you can compute the expression of the ciphertext blocks after encrypting some blocks of messages. And I hope these formulas are correct. But well, just have to identify some parts of it that you can leave as a constant, and then some parts that you can make vary, and some hidden shifts that are absorbed to that. So the parts we make vary are the blocks M0, and then this M0 plus M1 plus M2, and then M0 plus M1. And then you have values that are XORed to this, which correspond to our hidden shifts. This is what we will recover with the algorithm. The rest is left as a constant, and that's it. Okay, so we have to somehow modify all of this, these two blocks, to obtain our 1-bit output function. So we have some post-processing to do. We have to XOR the two blocks, and then we have to select 1 bit of each column, and then we have to make some assumptions. We have to XOR everything, and then we have to remap this to -1, 1. And because the AES round is so simple, in the end, that's really important. In the end, what you obtain is simply a function of 48 bytes inputs. And then this is a product of 48 different functions, which each time will have an S box and then some linear mask, some linear post-processing. And that's really nice because it is indeed a very simple function, just a product of 48 8-bit functions. Okay, so at this point, we have this Oracle query, and now we have to finish the algorithm. So we need to implement the computation of the Fourier transform, we need to estimate the success probability, and we need to finish the attack. So as I said, the function is simple because it's 48 functions and you take the products, and so the Fourier coefficients are easy to compute. They're easy to compute, and you can also compute the entire distribution of them. So you can exactly estimate the success probability of this attack, and it's going to be something around to the minus 30, which is not so large, but enough to have an attack. And then you have these shifts that the algorithm recovers, and then you just need to get the internal state from that, and you can. So all in all, and if you compute the entire cost of this attack, it will require you around to the 34 quantum queries, and then around to the 56 nonlinear quantum gates until you can find the secret key. Coming to the conclusion of this talk, what happened actually? Well, lots of quantum stuff, but the reason why we managed to break to do these attacks is that if you only observe the ciphertext, you obtain some kind of intractable systems of equations. You can't recover the state from that. But we get new information with the hidden shifts, and now the system becomes tractable, and now we can obtain some information. So in this paper, we did several schemes, AES-based AE schemes like ROCA, ROCA-S, and a version of AGIS. But I must say, of course, we obtained Q2 attacks, and we still expect these schemes to remain secure in the Q1 setting. So this our attack is very specific to the civilization model.
Thank you very much. Do we have questions from the audience?
Yeah, thank you. When you do this multiplication step in the algorithm, you say that to increase the probability, you need to cut small values. How exactly do you realize this cutting off of small values?
You take a bound, and then you do this rejection sampling operation, but only for the values which exceed the bound. And this covers this has to cover a fraction, a sufficient fraction of the total amplitude, so that it works. And you can compute exactly the success probability of this operation if you know the entire distribution of the Fourier spectrum of the function. So it's like it's an optimization that you have to make, otherwise the algorithm is going to perform quite poorly.
Right. More questions? I may have one. There was proposals of nonce-based AED scheme called QCB at AsiaCrypt that is secure against Q2 attacks. And I wonder the applicability of the technique here to QCB. This is not applicable, or this may be there is room for apply the attack because of the details of the model.
Okay, thank you. So short answer, it's not applicable to QCB because we had a proof of security against Q2 attacks, as long as you don't repeat nonces. And so long answer, what would happen actually is that I think if you look at QCB, it's basically theta CB. So it's based on a tweakable block cipher, and when you change the nonce, it changes the tweaks, and so you obtain entirely different permutations. And in the case of application of this attack is more when you obtain a different hidden shift. But if you already don't have an hidden shift, or if the entire function changes, then it really becomes a problem.
Thank you. So let's thank the speaker again.